now be stretched out in time, and even if you want to reintroduce the real numbers, if you absolutely want, you can do that at some moment. There is a real space, Rn, and the manifold has an open set. At that moment, that looks like an Rn. But you see, your manifold will be boom, exploding in the time and over a union of intervals that corresponds to all the points. So there is around the manifold a big interval now where the manifold lives, and at some moments you will have opens that look like Rns. Because in this non-commutative space I didn't put any other structure for the moment than the topology. If you want to think of this as vector spaces over the real numbers, fine, but not necessary. So there is a way to define all the structures now, at least philosophically, in this non-commutative world. It has of course a projection here that looks like a manifold, or the whole thing, that it should not be spacetime, it's any manifold is okay. The same story. And here also, so it projects here to something like a manifold. But in here it is a very strange manifold, of course. Even if it has locally real structures, it doesn't have it at the same moment. The same tricks as what I said to a point applies to a manifold. And you can go then introduce an analytical differential theory and so on, and smoothness. But this is a whole project. I didn't go so far. I was just trying to see what remains after everything has been thrown out. And this is what remains. This is where I end. So then maybe I'll give you a definition of stalk. So pre-sheaf. So let's say you have a partially ordered set at least. But if you want, you can think of a topology, and I will give the definition of a non-commutative topology at some moment, and we can do some more theory. But let's say it's at least a post set, and then a pre-sheaf is a functor from the opposite to a category, any category. Maybe you want limits, products, and some limits with limits. But usually it's a Abelian category, or I know why category was in decline for a while, because people were always saying, you just take the category that does everything that you want. A very good phrase, I will repeat it. Take a category that does what I say. And I don't know what that means, but at the end it may be nothing. But so okay, you have a pre-sheaf is just a functor. Then you need covers. That's why Grothendieck went to Grothendieck topology, just using covers. In a poset, you can define covers. So something like, if you want it, something like if gamma is bigger than kappa 1, then some elements, then so a cover means that, what does it mean? A cover is an element tau. Tau is a cover of these elements if this implies gamma bigger than tau. If something is bigger than the elements, it's bigger than the cover. Right, and if not if. So you can define even in a post set a cover. And so you don't have to go to topologies and so on. But let's assume that you have a normal notion of cover, like in a topology or a lattice or whatever. So that means that you have for some element U is a union of things. Then you have, by the functoriality, you have these restriction maps. Rho U, U alpha, I, let's call it UI, sorry, from the P, U to the P, U, I, let's call it UI. UI is U alpha, I. You have these restriction maps. Now assume that two elements, if I have two elements X and Y in PU, so that the restrictions are the same. So two elements that in all restrictions are the same, then they are the same. That's separated. So this thing means separated. And then the sheaf axiom is a gluing axiom. So that's the, maybe I should erase this if you don't mind. So separation is that two things go to the same thing in a cover, they're the same. And gluing means that suppose you have a union, let me write it topologically, yeah, with the symbols here, doesn't matter what I write here. Now assume that they are given xi in p u alpha I, so I'm using category here for notation as always, and assume that the restrictions from ui to ui intersection uj of hi is the same as the restriction from uj to the intersection. So you have a covering by certain opens. You look at all the smaller intersections and assume that you have an element, that you have a set of elements on every part of the cover that agrees on the smaller intersections. So there's a, what am I writing here? There's xi and here xj. So this is a condition. Assume that they agree on smaller intersections. Then they stick together. Then you can define a global object that maps to it. So then there exists an x in pu, in the global thing, such that the restriction of this x to the smaller thing is the xi. So you give xi's that are glued together on the intersections. It's very obvious when you think about it. Then there is a global element that restricts to it. You just glue it together. That's the gluing action. So the second action makes a separated pre-sheaf into a sheaf. So now, when you have a point of your space, a point in the whole space, then you can look at filter of neighborhoods in that topology. Or you look at all opens that contain it if you want. So you look at all the u's that contain x. So you do x, classical drawing, and you have always these opens. And over these opens you have it in the pre-sheaf, you have p, u, you have these things above it, these categorical objects above it. And then you go down and down and down, you go smaller and smaller so you have a filter of neighborhoods of x if you want in the classical terminology, but it's just a downwards directed set of opens in some topology or in the poset. And then you just, here what you have for, when you go smaller, when v is smaller than u, you have maps from pu to pv, and that is the restriction map, which we call, for example, rho uv. Right? So if I have a filter going down to a point, let's say, then I have a directed system of maps in the category. And since I assumed, which is good, that my category has limits, I need direct limits now, I take the direct limit of all these things. I take the direct limit of the pu, where u varies over the filter of neighborhoods of x, so all the u containing x. So this is an object in the category that corresponds to x in some sense, to the filter of neighborhoods of x. Now, if the topology is Hausdorff or T1, then for a given point, if you have 2 points, you can always separate the points by an open set. There's always an open near x that excludes any other point. So in that case, the filter that you look at, the descending chain of opens that goes to x, determines x, in fact. And then it's very, very intuitive to think that this